Okay. It's 6:30 p.m. here, so okay, now we should start. Would you please start?
Okay. Shall we start with part 2 for today?
Okay, so let's start.
Okay. Your sound is a little bit distorted, Byung-Yoon, but I hope you guys can hear me clearly.
Okay, I can hear you. Okay.
Okay. Then I will start. So we ended with a discussion of a CFT at finite temperature. And the first thing we studied in a CFT at finite temperature, computing aspects through its ADS formulation, through the GKPW formula, is a thermal phase transition if you put the CFT on a sphere. If the temperature is very low, you just get the finite temperature. You get a sort of a confined phase of the CFT. If the temperature is very high, you get a deconfined phase of that CFT. Now, one thing about finite temperature systems, and those who have studied a little bit of condensed matter physics notice, is that when if you study objects at finite density or finite temperature, and you're interested in their long range infrared physics at scales lower than the temperature, these systems have a universal behavior which you can describe in terms of hydrodynamics. It's just the dynamical equations for the conserved quantities. And the dynamical equations for conserved quantities are just the conservation equations of energy momentum. And if you have a charge in the system, the conservation equation of a charge. And in a relativistic notation, this is very easy. It's just the equations that you see here, the conservation of energy momentum and the conservation of charge. And one of the things we have learned, and I'm just going to state this for you, but there are many interesting papers, that this notion that hydrodynamics is the universal low energy theory means you have to go to usually to very long time scales, where these are the last time scales the longest time scale is the one that controls the hydrodynamic relaxation. But in a strongly coupled system, that time scale where hydrodynamics starts to apply is actually much shorter than in a weakly coupled system. And you sort of intuitively, you can understand it that strongly coupled systems, sort of individual excitations know a lot about other individual excitations, and the system collectivizes. It starts to show macroscopic behavior much earlier than a weakly coupled system, where a small particle can exist on its own or have its own motion much longer because it's less sensitive to what the other particles doing around it. And so what we're going to do is we're going to apply this idea of hydrodynamics to the finite temperature CFT. And the hydrodynamics is essentially the first deviation from equilibrium that you're going to study in a finite temperature system. So let me briefly review a little bit about hydrodynamics that you may know from other areas of physics. So specifically in relativistic notation. So we're going to use relativistic notation where I have a fluid velocity u mu, which is normalized such that the length squared of u mu is -1. It's a time-like factor. So there's a reference frame where if the fluid is homogeneous and at rest, there's a reference frame where u mu is just a 1 in the time direction and everything everywhere else 0. Now, this energy momentum tensor, if you have a perfect fluid, and a perfect fluid we will explain a little bit later, it's a fluid that shows no dissipation and just has strict entropy conservation in system, has a very simple stress energy tensor, which just has the energy in the 0,0 component and the pressure in the other diagonal components. And you can write that in a slightly different way of T mu nu is epsilon plus P times U mu U nu. This is the fluid tensor plus P times eta mu nu or G mu nu if you put it in a more general background. And to solve the equations for a perfect fluid, you need one more equation, because if I have no charge, there are 3 + 1, 4 equations here. If I work in 3 + 1 dimensions, right? But I have 5 variables here. I have the 3 variables u mu, because one of them is constrained. I have epsilon and p, and that gives me 5 variables. So I need one more equation to close the system. And that usually is the equation of state, which determines the pressure in terms of the energy density. And then I have a system for 4 equations and 4 unknowns, and I can solve the system. So this is the sort of a very brief review of simple relativistic fluid dynamics. However, as I mentioned, this is a perfect fluid, and in real life, fluids are not dissipationless. You can have entropy creation in this system, and entropy is precisely related to sort of the first corrections to the fluid, to the perfect fluid expression. And these corrections are expressed in terms of gradients. Here you see there are no derivatives of gradients of the fluid velocity. So that's how you can really see that this is a low energy expansion in pure equilibrium. Pure equilibrium, of course, has no entropy generation because the entropy is constant there, right? It has no gradients, and then you go back in the perfect fluid situation. But if you have gradients in the system, these will cause diffusion in the system. The diffusion is associated with dissipation of energy and momentum into the bath, and that's how the system relaxes. And just simply based, if you have a homogeneous and isotropic system, based on the symmetries of the system, you can have a trace part of the spatial stress energy, which has an independent coefficient, and then there's an sort of a traceless part, which is just the representations under the SO3 rotation symmetry that remains. Remember, I have a fluid now, I have stuff, I have a fluid velocity, and so that breaks the full Lorentz symmetry, but I have a remaining SO3 rotational symmetry, and I classify the derivatives of the fluid velocity in representations of that SO3. So in this homogeneous, there are 2 new coefficients that appear in these are called the constitutive relations, and this is called the shear viscosity, and this is called the bulk viscosity. And the way they now enter into the system is that if you now put a small perturbation in the system, you can show that transverse momenta, right? In other words, if I put a small momentum in the x direction, it will relax in the y direction exponentially with an exponential rate controlled by eta. This is the shear viscosity. Or you can have a decompression, which is just an overall pressure change, and this will relax back also exponentially with an exponent controlled by the parameter zeta. So eta and zeta, these are called transport coefficients, and they're also decay constants of how transverse momenta and decompressions relax in the system. And what we're going to do is we're going to compute the shear viscosity of a CFT at finite temperature in such a system. We're going to compute what this number is. So in a normal system, and there are famous computations that you may have done in statistical mechanics, where you start with a classical dilute gas, and you can compute these transport coefficients from the Boltzmann equation. We cannot use a Boltzmann equation. We don't have an underlying weakly coupled particle picture, but there are nevertheless ways that we can compute these transport coefficients. And the reason we're going to compute the shear viscosity is extremely simple, is you can prove, because this object is controlled by is about decompressing, so it's about scaling transformations. In a CFT, the bulk viscosity is always zero, just from the underlying scale invariance. So in a CFT, the only non-trivial transport coefficient in a system that has no charge is the shear viscosity. So that's the object we're going to compute. Now, how are we going to compute that? How do you compute this shear viscosity? And I'm not going to give you the full derivation. I'm going to give you a slightly simpler derivation of how to compute another diffusion constant. And then by analogy, I'll give you the exact expression of how to compute the shear viscosity. And so for simplicity, let's not consider the conservation of energy momentum, but let's consider the conservation of charge. And so what happens, like I said a moment ago, is what you imagine is that I have a fluid which is sitting here, and locally I add a little droplet of charge. Well, you know intuitively what happened, that droplet will spread out, it will diffuse, and will get absorbed in the system, right? And that absorption is associated with a dissipation, right? There's entropy creation, and you don't see that little bump of charge after some time anymore. And mathematically, the way this is encoded is the following way. This is called Fick's law. Is that if you have a current, right? This is the background charge density, right? That if you put a local gradient, put a local blob of charge with it, that creates a current, right? And the current is proportional to the gradient in the charge. If there's no gradient in the charge, there's no current. This is precisely analogous to this gradient term in the fluid velocity here. Okay. And there's a coefficient d called the diffusion constant, right? Which tells you the strength with which this current is generated, right? And simply using the fact that the charge is nothing less than the background charge density, J0, I substitute that in here and I get a relation between Ji and the gradient of J0. And now I take the divergence of both sides. I take di of both sides. So I take di of j. This is then minus d times the spatial Laplacian of J0. And the last one I need is the charge conservation. That means that d0 J0 plus di is 0, or in other words, di Gi is minus d0 J0. And then you obtain this equation. And this you recognize, this is dt now. dt G0 is a coefficient d times box J0. This is the heat equation or the diffusion equation with d, the diffusion constant. So here you see how from a small perturbation in the system, you get the diffusion equation if you assume Fick's law. Okay, and as well known, if you solve this in Fourier space as a function of t and a function of the spatial momenta k, you get a decay, that's the diffusive decay, controlled by the diffusion constant d as a function of k squared t. Now, this diffusion is also related to the conductivity. The conductivity is the actual transport coefficient that appears in the constitutive relations. And it's related through the so-called Einstein relation, with chi0 is the static susceptibility. It's how if you change the charge of the system a little bit, how the chemical potential of the system reacts to the system. So the viscosity is like a conductivity, but it's related to the diffusion constant and a thermodynamic equilibrium quantity called the static susceptibility. Now, what we want to do is we want to compute this object sigma. We're going to compute the transport coefficient. And we can do that from this same point of view of the same knowledge about the heat equation for J0. Let's show how that works. Let's now Fourier transform both sides of the equation. So I get minus I omega J0 is dk squared J0 of omega k. In other words, J0 as a function of omega k obeys the dynamical equation I omega minus dk squared is 0. Now, if you have a more complicated general situation, right, where you have higher order terms of J0 or something like that, you know how to solve this. You would construct the Green's function, the 2-point function of J0. And you know that if this is the equation of motion, then the Green's function is 1 over I omega minus dk squared, because the Green's function obeys I omega minus dk squared is a delta function, or is a unity. And there's a slight subtlety here, which is important if you want to get the right answer, is that this is semi-classical physics. There's no quantum mechanics here, right? So the only proper Green's function in the system, in a relativistic system, is the retarded Green's function, right? That's the one which respects the causality of the system. The retarded Green's function is in a very simple way, it's the Green's function which only has decaying responses once you Fourier transform back to real time and decays towards the future. Now I can do a mathematical trick. I can look at the imaginary part of I times G. If I do that, that is proportional to dk squared over omega squared plus d squared k to the 4. And if I now I can extract the number d from this equation by taking the following combination. I take k squared imaginary ag, and I take omega to 0. This is precisely proportional to 1 over d, because it becomes dk squared over d squared k to the 4th. The k squareds I've adjusted to cancel, and I get a number of d. Such a relation is known as a Kubo relation, named after the famous physicist Kubo, which shows you how from the imaginary part of the 2-point function, a fluctuation relation, right? 2-point function is about fluctuations. You get information about how the system dissipates, right? This is the diffusion constant, which is relation to the dissipation theorem. So this is a corollary to what's known as the fluctuation dissipation theorem in the system. And the fluctuation dissipation theorem is also related to the optical theorem in electrodynamics and other objects, where you look at the imaginary part of Green's functions. Okay, so the general rule is that to extract diffusion constants and transport coefficients, you have to study a little bit the hydrodynamics and construct an appropriate combination of the imaginary part of the Green's function in a limit for omega 0, and the remaining value is the transport coefficient. And this is very general, and it doesn't rely on an underlying Boltzmann equation or a particle picture. The only thing I need to know is what the 2-point function of the conserved currents are. In other words, this is a way to extract the transport coefficients without having without needing to rely on the microscopic picture of where those transport coefficients originate. So that is what we're going to do. We're going to compute the viscosity from an analogous Kubo formula. And like I said, it's a little bit more tricky to derive this one, but it's not that hard. But I'm just going to state it here for you. So the viscosity is extracted from the retarded Green's function of the stress energy tensor, right? Which is formally the following object. And this theta t is precisely the term that ensures that this is only a response towards the future, and therefore has, if you would Fourier transform this, had only decaying tails and never growing responses as a function of time. All right. And then I need to divide by an extra 1 over omega. That's one of these manipulations that you have to do. And then out just rolls minus the viscosity. So if I can compute this correlation function by running it through this machinery, I get the value of the viscosity. And now we're in business. This is why the Kubo relations are important in ADS-CFT, because this object here, leave these things, this is just a 2-point function. Right? And 2-point functions are precisely the objects that we know how to compute now in ADS-CFT. using the GKPW rule, how to compute correlation function in the CFT from its ADS description, we can just apply that to compute this object here, and then from that extract the viscosity. So that is what we're going to do. Now we're going to apply all the knowledge that we have. So the first thing we have to do is we have to compute the two-point function of the energy momentum tensor. Now the energy momentum tensor is an operator in the CFT. So we need to identify what is the field that is dual to T mu nu. If there's a question, please don't hesitate to interrupt me. So the field that's dual to T mu nu actually is just the metric itself. It's G mu nu, which is easy to see by its tensor properties. This is a symmetric tensor in symmetric 2 tensor, and the natural object that's a symmetric 2 tensor on ADS is the metric itself. Of course, as we know from Einstein's relation, from general relativity, of course, G mu nu is also associated to energy. So from that point of view, it's also the obvious object that is there to compute. So the field that we should consider in ADS is just the metric field itself as a dynamical field. And so the action that we need is just the Einstein-Hilbert action with a cosmological constant. And then we have to perturb it in the right way. Now, the one thing that is I haven't emphasized here, right, is that the object here that you want to compute is the stress tensor in the x1, x2 direction. You want to compute this at the 0 momentum, but actually it's easier to compute this at a finite momentum in the x3 direction, and then to let that momentum go to 0. And the reason is the following. That
Professor, I have a question.
Yes.
In 3.16, you map this G mu nu in the bulk side to boundary to T mu nu.
Yes.
And but in the equation 3.3 in your previous slide, 3.3, where you represent this energy momentum tensor for fluid. Yes, there are also some G mu nu.
Oh yeah, this is a different G mu nu.
Okay.
My apologies. This is the metric where the fluid lives. Okay, that should have been, I should have put eta mu nu here.
Eta mu nu is.
This should be eta mu nu.
Okay.
Whereas this G mu nu is the dynamical metric in ADS.
Thank you.
Okay. Okay, and an easy way, or the way to see that what I said, that you should put a small momentum in the x3 direction, is then you can simplify the problem a lot. And the simplification goes as follows. And I'm going to use I'm going to use a specific space-time dimension ADS5 as an illustration of this. Right? So ADS5 has a radial coordinate, a time coordinate, and 3 spatial coordinates along the boundary. And let's take my G mu nu, right? And I take a background and I perturb it a little bit. Remember, I want to compute correlation functions, so I need to perturb it a little bit, and that's the object that's of which I want to compute the two-point function. Now, if I have a small momentum in the x3 direction, or a small spatial profile in the x3 direction, but not in any of the other directions, right? Then what I'm left over with is an SO2 rotation invariance in the plane x1, x2. I can arbitrarily rotate around the x3 direction in the direction x1, x2. And that means that there is a remaining symmetry, despite the fact that I have an arbitrary perturbation here. And I can classify all my excitations on the representations of that remaining symmetry. And then by the usual symmetry rules, they cannot mix with each other. And so if I do that, I have a very simple, there's a 2 tensor, which has both the directions x1 and x2. There are vector perturbations, which have precisely 1 index in x1 or x2. And there are scalar perturbations, which have no indices or actually have double indices in the direction x1 and x2. Okay, and remember that for the shear viscosity, we needed to compute the stress energy tensor in the direction x1, x2. And you see what the nice part about making this, introducing this X3 is that I only have to consider a single component of my variation around my background. I can set all these other components consistently to 0 from the beginning. As you know, when you take a small variation of the metric, right there, thanks to the Christoffel symbols and the Ricci contraction, there's a lot of stuff that you have to carry around. But if you can simplify it this much, a lot of that extra stuff immediately vanishes and goes close to 0. So that is the great advantage of giving it a small amount of momentum in the X3 direction. And at the end of the day, we first set the momentum to 0, and then we take the momentum, then we take the frequency to 0 in a very in an appropriate way. So we only need this tensor perturbation, which is a single field. And let me Fourier transform it. And then in order not to carry all these indices around all the time, I'm going to call this field phi. Okay. And then without computing this, I'm just going to state it, that if I look at the linearized equation, the motion for this object with tendons, with the two tensor indices x1, x2 in this particular way, and I call that the field phi, then after a little bit of work, I can show that this is precisely identical to the equation of a massless scalar, right? A massless scalar which only has excitations in the r, t, and x3 direction. If it would have excitations in another direction, it would not be true. But if I limit it to this, then this is correct. And this is now very easy because we've already solved the equations for even massive scalars and how to compute 2-point functions of massive scalars in ADS-CFT. So we can apply all the machinery that we already learned to do so. So let's go ahead and do it. Remember, we're studying hydrodynamics, we're studying the system at finite temperature. So the one novel ingredient is that we don't substitute in the ADS metric, but we now substitute in the ADS Schwarzschild metric. That means that the radial equation, I Fourier transform in T, I Fourier transform in K, and the radial equation now looks as follows. And I'm using a Poincaré, ADS Schwarzschild, and I've generalized again to D dimensions. Okay. Now, again, we do the same as before. We denote the near boundary behavior of phi in terms of the leading coefficient A and the subleading coefficient B. And you have to be slightly careful now. Before I had z to the power delta minus, but I'm now using the ADS Schwarzschild coordinates where r is basically 1 over z. So you get r to the minus delta minus. And here I get r to the minus delta minus minus d. And I'm going to carry this delta minus around to emphasize the analogy with the previous case. But remember, for this very special case of a massless scalar, delta minus, which is equal to d over 2 minus the square root of d squared over 4 plus m squared, but m squared is 0. So the square root of d squared over 4 is d over 2, and d over 2 minus d over 2 is 0. This is a very special case where delta minus is 0. Okay. So there's also in this particular case no counter term to worry about. But anyway, we know that once we have solved the boundary behavior like this, the retarded Green's function is just the ratio of B over A. And we're done, right? So once I solve this, B over A is done. You can do this. It is very straightforward. We've done it already. You only have to be a little bit careful that the equation you now solve is not the Bessel equation, it's this finite temperature equation. And you can do this numerically or you can do this semi-analytically. But we're going to actually compute the retarded Green's function in a slightly different way, which at the end of the day is the same result. But using a trick, there's a convenient way to compute it. And the trick has some physics in it. So let's see how we're going to compute this Green's function now in a different way. Okay. Remember, fundamentally, this B over A came from the following expression, that the CFT Green's function is the normal derivative, the derivative in the radial and the RS direction of the solution divided by the solution evaluated at the boundary, with here the appropriate r to the minus 2 delta minus, even though delta minus is 0, right? And then you have to take these metric factors with you. There's one small extra thing that I'm going to add here, is because this field phi is really a component of the metric. The coefficient is not 1/2, but it's 1/2 kappa squared, where kappa squared is the Newton's constant that is in front of the Einstein-Hilbert action of general relativity. In other words, it's equal to kappa squared is 8 pi g Newton. All right. So this is the fundamental expression, which is in essence exactly this expression that we had before. But rather than solving phi and substituting a and b, I'm going to do one step first. I'm going to use the fact that I'm not interested in g itself, but at the end of the day, I'm interested in the imaginary part of this Green's function. Okay, so let's compute the imaginary part of this Green's function. And I'm going to do that after I just multiply this by 1. And 1 is just phi star r divided by phi star r. Okay, and then here you see phi star r divided by phi star and the derivative. And to take the imaginary part, I subtract the complex conjugated and divide by 2i. Okay, so the imaginary part is precisely proportional to this object. And now you recognize something that we've already seen before. This numerator here is what's known as the Wronskian. Okay. I already mentioned before that the Wronskian appears just in the theory of differential equations to either normalize the Green's function or to show that you have independent solutions. But in physics, the Wronskian also has a very important medium. It measures the flux density through a surface. In that sense, it's related to this fact that the imaginary part is proportional to the Wronskian, is directly related to the fact that the imaginary part of the response in electrostatic calculates the absorption rate of a material. And that absorption rate is nothing more than the flux density that does not get reflected. Now, what is the associated with this flux density is a conservation equation. So if you have a field obeying a second order differential equation of the following type, the Wronskian itself is not conserved, but it's e to the p of this Wronskian, or actually more appropriately, the Wronskian is e to the p of this mixed derivative term, and that's the object that is conserved. Now, I'm not going to state it for you, but it's not so difficult to see that the combination square root of minus g GRR is precisely the prefactor that is associated with the equation of motion for this massless scalar field, right? Here you see it in essence already. So what that means is that I can write the imaginary part of the retarded Green's function as 1/2 kappa squared. It's this limit where I take the cutoff to infinity. And this whole numerator here, including the square root of minus g GRR, is just the Wronskian that is associated with the equation of motion. Okay, and then I still have to divide it by 2i times the absolute value squared of the solution. And this is the trick we're going to use. We're essentially going to use flux conservation here, right? The fact that this w, even though I wrote it as a function of r, secretly it doesn't depend on r. And therefore I can evaluate this numerator anywhere I want. I can evaluate it at the horizon, I can evaluate the boundary, I can pick what is the most convenient place to evaluate it. And that's the trick I'm going to use. You clearly see that this is a trick that doesn't apply to every single correlation function, but for this particular correlation function, or strictly speaking, any correlation function that has to do with a conserved current, and h mu nu, right, is a fluctuation of the metric, and that has to do with conservation of energy. This trick is very useful. So that's the guideline when you can think of using this trick or when not. So let's use the conservation of the Wronskian to evaluate the numerator. And the place we're going to evaluate it is at the horizon, because that's where it is easy to evaluate. And let me show you that. So near the horizon, this emblackening factor that's in the metric is r minus r naught times d over r naught. And the equation of motion for phi reduces to the following combination. I have the double derivative with respect to the radial direction. I have 1 over r minus r naught, a single derivative. L is the radius of ADS, and only the frequency part survives. And that's because precisely the frequency part has an extra factor of f, the dt part. Here you see it, whereas the k squared part does not. So when f is 0, near the horizon, you see something very interesting, that the momenta, it doesn't care what the momentum of this field phi is. And there's a factor of 1 over f squared on the bottom here. So near the horizon, this is essentially what the equation reduces to. Now I follow the procedure as before. Let's look at this the most general solution to this more simplified equation. That has 2 characteristics exponents, right? I deduce them by making an ansatz that phi solution is itself r minus r naught to some power alpha. And then you see that alpha obeys the following equation. The 2 derivative term gives you alpha alpha minus 1. This is the single derivative term, and this is the term that remains here. And all the r minus r naught factors can be divided out. The characteristic equation has 2 solutions. Alpha is plus or minus I omega L squared over dr naught. And now the one thing I am going to do is I'm going to use the expression for, or the relation between r naught and the horizon temperature, what we derived earlier this morning. And if I do that, including the factors of 2 and pi, I find that this is nothing more than plus or minus I omega 4 pi times the temperature. And now you have to pause 1 second, because which is the solution that you should pick? You know, as I mentioned earlier, or as we actually had a bit of a discussion about yesterday, is one of the boundary conditions for the solution is determined in the interior. And in this case, we have a horizon, so that's where the boundary condition is determined. But I still have 2 options. I have to pick one. Now, from the ADS point of view, there's a very natural one. I have a black hole. A black hole attracts. So I should choose the solution that falls in. That seems to be the one that should correspond to ordinary physics. And if you trace back to the expression for phi, what that means, it means it must move into the black hole as time evolves forward. And that is the solution with alpha is minus I omega over 4 pi t. That seems like a good choice. I just consider it from the ADS. Fortunately, this is completely supported by what this means on the CFT side. If you stick this in and you compute now the 2-point function, right, it turns out this is exactly the retarded Green's function that comes out. You can study this in several different ways. The easy way to study this is to show that in the complex frequency plane, all the poles are now below the real axis. And that's one way to define the retarded Green's function. Slightly more tricky way is to show that all physical responses decay as time evolves towards the future. Okay, and there's a beautiful story how you can deduce that this is the retarded Green's function. In fact, the other solution, which once you realize that the advanced Green's function is the complex conjugate of the retarded Green's function, you realize that the other solution of alpha gives you the advanced Green's function. So this answers actually one of the particular questions is you have 2 boundary conditions in the interior. Which one do you pick? And you have to think a little bit about it. In pure ADS, it's just regularity. You don't want there to be a singularity. But at finite temperature, when you have a horizon, right, the different solutions correspond to choosing a retarded or an advanced Green's function. And usually the object that you're interested in is the retarded Green's function. In fact, for the Kubo relations that we want to use, one is specifically instructed to use the retarded Green's function. So that is the object that we want to compute. Okay. Okay. So this was the near boundary behavior of phi, and we know it's near boundary exponents. And so that means that the general solution we look at has a near boundary behavior of minus I omega divided by 4 pi t times some function of r of r naught, where we know that to leading order as r is r naught, f is a constant plus higher order terms in r. Okay, or to put it in more fanciful words, f is regular at the horizon, r is r naught. It doesn't, neither has a zero nor has a pole at the horizon. Okay, so this is the type of solution that we're going to seek, and this object f is still not determined. Okay, here I write it again. Okay, but now I can use this to evaluate the conserved Wronskian. Remember, this is the Wronskian, and since the Wronskian does not depend on r naught, I can evaluate it at any r, and let's evaluate it exactly at the horizon. So the object I have to compute is to compute this mixed derivative, right? With substituting this in, and I leave f for the moment. I leave undetermined, but at the horizon I know it's just a number. So at the horizon I can ignore the derivative acting on f, and it's just a constant, and then the derivative only acts on this prefactor. So if I substitute that in, I get this r to the d plus 1 over L to the d plus 1, the G inverse GRR, the inverse warp factor, and this derivative gives me this following term, an r minus r naught inverse times the f, the value of f at the horizon. Okay, and then I really have to evaluate this strictly speaking at the horizon. So the right way to think about it is I should take the limit of these prefactors. I've taken the limit to the horizon of the fields phi here, but I've not appropriately taken the limit of the prefactors here. And when I combine that and simplify that, that gives me this combination: d over r naught minus 2i over 4 pi t times these factors. So this is the value of the Wronskian, and not only is this the value of the Wronskian at r naught, it's the value of the Wronskian everywhere. Okay, so this is now what we're going to substitute in expression for the Green's function to compute the shear viscosity. So let's substitute this in the Green's function. Here was the formal expression for the Green's function that I had a moment ago, right? That was minus 2 delta minus WR over 2i f sol r, okay? And then if I substitute this in, delta minus is 0, all right? And then I substitute the value of the Wronskian in, I get this as the final answer for the story, where I've changed all the expressions of r naught over L into powers of t. And this is an omega. And there's one thing that I have done here is this phi star sol. This should be equal to still a field of phi star sol. This should not be f yet. We will see in a moment what the f is. But what I do need to do is need to know the ratio of this f star 1 times f, the absolute value of f, towards the absolute value of phi, or at the boundary. And it's not so hard to see that in the limit of omega going to 0, k going to 0, the leading contribution will be the omega independent solution for the remaining function f, right? And if you look at what this function, this is the full equation of motion. If I take omega and k is to 0, this guy dies, right? And so I get a very simple equation, which is just 5 prime plus phi double prime. This has a trivial solution where phi is constant. Okay, and so it tells you that the trivial solution in the limit omega going to 0 and k going to 0, right? That solution is a constant, and you can actually show it exactly equal to the same constant that is the value of f at the horizon. So therefore, I know that the imaginary part of the Green's function is just this 1 over 2 squared, and now I can take the limit r to infinity in this system, because this constant now divides out, and I just have a minus omega and a 1 plus higher order in omega terms. For the shear viscosity, we're going to only need the lowest order in omega terms. So these terms I can ignore. And now we're basically there. Because remember, the shear viscosity is proportional to the imaginary part of this retarded Green's function, plus some extra factors. And then we get out the answer that we seek. So let's do that. From the Kubo relation, this is the Kubo relation. This was the answer. This is 1 over omega, the imaginary part of this retarded Green's function, and the limit omega going to 0. So the only thing I have to do of this previous expression is drop the minus omega term, and I have my answer for the shear viscosity. This is the shear viscosity of my CFT that lives in a certain number of dimensions, expressed in the temperature of the CFT. Now I still have an ADS radius here, and I still have G Newton here, right? Now remember that if you use one of these more concrete examples of ADS, that there's a ratio of these length scales. This is the basically dimensional constant, which is proportional to something like G squared Yang-Mills NC. So that's how, in the end of the day, you relate this to quantities that are only expressed in the CFT. But I'm going to leave it like this as well. So the main thing you see is that the shear viscosity increases as a positive power of the temperature. The higher the temperature, the more viscous this system is. Now, the gentleman who computed this for the first time, Polycastro, Son, and Starnets, they very quickly, together with Pavel Kovtun, realized something very interesting, is that if you look at the entropy density for such a black hole doesn't only have temperature, but there's a famously black holes appear to obey all the rules of thermodynamics and therefore also have an entropy, right? The entropy is of the following type for such a d plus 1 dimensional ADS Schwarzschild black hole. And this temperature dependence on both sides is nearly identical. In fact, the gravitational coefficient is also nearly identical. Well, if you take the ratio of these two objects, you just get a number, which is 1 over 4 pi. And if I actually restore the proper units, right, this is 1 over 4 pi h bar over kb, right? The units of this is seconds divided by Kelvin, right? So this, the interesting part is that this is an object which is just related to fundamental constants. Right, all the properties of the theory have disappeared, and this should make you think of something where there are also sort of only fundamental constants appear. In particular, what happens is that the gravitational constant drops out. So this seems to be a constant that is not very dependent on G squared Yang-Mills. That's not quite correct, right? This is the strong coupling result. We actually know that at weak coupling, where you can compute the viscosity using a Boltzmann equation, that's what I mentioned before, that the viscosity goes as 1 over G squared log G, where G is the coupling constant. So what this really means is that as you increase G, right, as you increase G, eta gets lower, right, at fixed temperature, right, or particularly this ratio gets lower. And then it asymptotes to a finite value, which in the limit of infinite coupling is precisely this ratio of 1 over 4 pi. Now this suggests something rather deep. Remember that a perfect fluid is a fluid where the viscosity in some ends under 0, right? And this tells you that actually a weakly coupled system is actually, you might think that's a good fluid, but actually is a really poor fluid. It has a very large viscosity, right? But a strongly coupled fluid seems to approach a perfect fluid, but in this limit, it appears that you can never ever reach it, right? It seems to asymptote to a finite value. And this gave rise to a very deep and powerful conjecture that has caused a lot of excitement in the field and a lot of follow-up work. So Kovtun, Son, and Starnets actually conjectured that this is a lower quantum bound on the viscosity, right? Like eta over S is something like, is always bounded from below by 1/4 pi over h bar kb. And you can do some very simple tricks with sort of a weakly coupled gas, helium, nitrogen, and an ordinary sort of real fluid, a liquid water. And you see that indeed, this object don't even come close to this viscosity bound. So real fluids obey this. But the whole point is that they were inspired by this, by a rather deeper point of view. Think of the Heisenberg uncertainty relation. Right? There seemed to be some quantum bound in the system, right? And the idea is that, of course, that in a real fluid, in a quantum fluid, right, you always have small fluctuations in the system, and so the gradients on average are never zero. And so you always experience some kind of viscosity in the system, even in equilibrium. And that means that there's always a minimal amount of dissipation in this happening in this system. You simply unavoidable. And this is also related to deeper notions that already in the early days of quantum mechanics, Einstein, who was very well versed in fluid dynamics, a lot of general relativity is based on fluid dynamics, right? He also thought that quantum mechanically there could be a lower bound on diffusion, precisely because of the fact that you always have small fluctuations, and any small fluctuation will eventually have to die out, right? And so there's always this lower bound on the diffusion that must always be present. But if this really is the lower bound, it implicitly assumes that the object we've just computed, which saturates the bound, is sort of the most perfect fluid. It's still imperfect, but it's the most perfect or the least imperfect fluid that there is in the system. Okay, and this caused a lot of excitement in the system. As I said, people already looked for these diffusion bounds for decades, and this was an extremely good candidate. And a second reason why people were extremely excited is roughly around the same time that these three physicists computed this number, came the first results of the relativistic heavy ion collisions, first in Brookhaven and then in CERN. Now, relativistic heavy ion collisions are related to QCD. QCD is a Yang-Mills theory, and in particular, it's related to the strong coupling regime of this non-abelian gauge theory, which nobody knew how to compute, certainly not in a dynamical setting. You could, at that time in the lattice, you could compute equilibrium properties, but it was very difficult to compute dynamical quantities. But you could now measure them in these heavy ion collisions. And what they found is in that the quark-gluon plasma, sort of the fluid, the deconfined fluid that they found in these heavy ion collisions, indeed had a viscosity to entropy ratio, which is very close to this universal bound, right? So it seemed to be a strongly coupled quark-gluon plasma, a strongly coupled quark soup that they found in these experiments. And this caused an enormous amount of fruitful interaction between people who are doing ADS-like computations and the heavy ion community. That was my lecture for the second part. Any questions?
Yes, Professor. How to measure the entropy density in experimentally? I don't know. We can measure the entropy.
Okay, so the interesting part is that if you have a system which has no charges in its system, no global charges. So QCD, of course, has color charges, but these are gauge charges, no global charges. Then you can simply use the fundamental relation of thermodynamics to relate T times S to epsilon plus P. So this is also related to the ratio eta over epsilon plus P under the assumption that there are no charges in the with an extra factor of the temperature.
Okay.
So the epsilon you can measure, the energy density you can measure, and the pressure you can measure. But it's even stronger than that that particular ratio of eta over the energy density plus the pressure is directly related to the sound attenuation constant in a system. In fact, that is this earlier relation that I showed earlier, right? If you there's this Einstein relation between the charge conductivity and the charge diffusion. There's also an Einstein relation between the shear viscosity, right, and the pressure susceptibility. And the pressure susceptibility is just 1 over epsilon, it's simply epsilon plus, or the energy density plus the pressure. And this diffusion is then the sound attenuation constant. And so by simply measuring how sound attenuates, you actually, with an extra factor of t, you directly measure this ratio. So that's how they measure it.
Thank you, Prof.
Any further questions? No questions? Everything was crystal clear? I'm happy to discuss also other things about yesterday's lecture or any other questions about ADS.
Excuse me, I have one question.
Yes.
In this slide, you said the system gets as the couplings gets stronger, the system's approach to the perfect fluid, right? And I'm confused because the strong coupling means the strong interaction between the particles, and I thought the system gets more viscous because of the interaction. But,
yes,
I misunderstand something. I don't know.
That's a very good question. So the notion of what a viscous fluid is, sort of in your intuition, like honey is viscous and water is not viscous, right?
Yeah, sounds counterintuitive.
It's a bit counterintuitive how to relate it to this the shear viscosity constant. In fact, in gases, or an ordinary gas, which you can also describe as a fluid, is actually extremely non-viscous in this language, right? And the reason is that this object of viscosity is related to your normal notion of viscosity, but it's not exactly the same thing. So this viscosity, the easier way to think about this number eta is it's how, if you have a small momentum perturbation, so I put some small momentum here, how it translates to the left or to the right, not forward, but to the left or to the right. Okay.
I see.
This is clearly related to the viscosity, right? So because if you have a viscous system, if you try to pull it, it immediately pulls a lot of the stuff with it.
Right?
Yeah. And the point is that this is related to the conductivity of that momentum. And so in a gas, this conductivity is actually very poor, right? If you take a gas and I take a gas, a single atom, and I give it a kick here, it's going to move forward. It's not going to easily drag the gas molecules with it.
I see. Yeah.
And so that means that the viscosity actually is in this object is the transverse momentum conductivity is very high, because this momentum conductivity shoots up, right? It does not get held back. Whereas if I'm in a strongly viscous system, it's going to be held back by the other object and move forward, right? So the transverse momentum conductivity in these objects are the other way around. And if you follow this argument through, and you see even I struggle here on the spot, you get the ordinary relation of viscosity. But the easiest way to think about it is that this is the transverse momentum conductivity. Is how a piece of transverse momentum gets conducted, so the momentum here, how it gets conducted to the left. So in a gas, it gets conducted very poorly, right? So now I'm getting myself again tied in knots. Whereas in the ideal liquid, it really rapidly transfers it to the right hand side.
Yeah, but I see. Yeah, thank you.
You're welcome.
You know, you just came to the formula by Kofton, Son, and Steinitz.
Yes.
And I assume that you'll be taking that into Planckian dissipation and strange metals and things like that tomorrow. But if you, since it seems like we have a little extra time, I'm just anxious if you have anything that you wouldn't necessarily get around to tomorrow in that direction with strange metals, linear resistance, Planckian dissipation, if you have any time to discuss anything off the top of your head, I'd be very interested.
Okay, I can say something a little bit. So this is then a small preview to, indeed, I'm going to go to strange metals in the next lecture, but I'm not going to discuss much on the fluid dynamics of that. So this actually is a very good point. So I can discuss it very briefly here. Now, what is one of the objects that people are interested in? It's strange metals. They are related to high temperature superconductors. Strange metals indeed are believed to have what's called Planckian dissipation. Now, Planckian dissipation, and the idea is that these ADS type theories are actually extremely good ways to understand the physics of these strange metals. Now, strange metals are also considered strongly correlated systems, and they also have all kinds of interesting behavior. And one of the objects that they found is the following. The reason why you get that this eta goes 1 over g squared is eta essentially goes as the cross section of two colliding particles. The cross section goes as the 1 over g squared, and you can relate it directly to the inverse collision time between the systems. Now, the inverse collision time in a finite temperature system is naturally expressed as the temperature times some function of all the other scales. And there is a similar idea before Kofton and Son and Steinitz came around, that there should be sort of the most strongly coupled or the most nearly perfect liquid is an object where this collision time is precisely h bar times the kb, sort of the inverse collision time is precisely kbt divided by h bar, with no other times. This is the shortest possible collision time that you could have in a system. Now, realizing that in a normal system, the viscosity is proportional to the collision time, you would get a viscosity that grows linearly in the temperature. All right, if you have a system that obeys Planckian dissipation, right? And so if you look here, these objects generically don't Planckian dissipate. They don't do here. But this object that I'm describing here is not a strange metal, right? Because a strange metal is characterized, and people can measure this by in real experiment by the fact that the entropy grows linearly in the temperature. But now you're back to the story. We've just argued that Planckian dissipation are objects that have a viscosity that's linear in the temperature. But strange metals, right, are also objects that by measurement have an entropy which is linearly in the temperature. And so the ratio, again, is temperature independent. And that was also the insight, as I argued here, for these gentlemen to construct this ratio. And so, although nobody has been able to measure the viscosity in the right way in a strange metal, so nobody can do this measurement yet, but the guess indeed is that these strange metals are also objects that are very close to saturating these bound. But the underlying physics is qualitatively related, but quantitatively a little bit different. It's more related to this saturation of this collision time, the Planckian dissipation, and the fact that you have a linear in T tempered entropy density in the system. Okay. So the linear in T entropy density we will actually see tomorrow, but I will not discuss the viscosity in this system. So this is a very good question, but it's a small preview of tomorrow's lecture.
So we're not quite there yet.
Does this answer your question?
Well,
the main thing is you can try to measure the viscosity, right, in these strange metals and whether it indeed is the right value. There are several ways to measure the viscosity, right? In this quark gluon plasma, you could measure this ratio directly by the sound attenuation constant. This you cannot do in strange metals, right? Roughly speaking, a strange metal is an object that lives in an atomic lattice, and all the sound perturbations are dominated by the response of the atomic lattice, not by the metallic degrees of freedom. So you have to measure it in a different way. And people are thinking about it. And remember, this is a fluid property. So somewhere they have to get the electrons to behave themselves as a fluid. This is even a bigger problem because electrons in ordinary metals don't behave as a fluid at all. They behave more as a ballistic, nearly free gas. But people now know exotic systems like the graphene or other, I forget the name of it, other systems with a hexagonal lattice, two-dimensional systems with a hexagonal lattice that are extremely pure, that have very little impurities in the system, where they can actually get the system to where the electrons start behaving like a fluid. And this gives then people a leg up or a first insight in how to try to measure the fluid properties of these electrons and whether they behave as a fluid. So this is an active area of research, but the high temperature superconductors, which have this strange metal phase, are notoriously fickle materials where it's not so easy to do these experiments.
Thank you. To get the linear resistance, is it enough to have the entropy be linear? I mean, related to the temperature.
Yes, so this is actually some work that I did in the past, and we are actively pursuing right now. You can show actually that in a very general way that in precisely oddly enough because of the presence of the atomic lattice, that if you put such a strange metallic electron liquid in an atomic lattice, that for very general principles, the resistivity in the system is proportional to the viscosity. And actually, this is it's very closely related to what I said a moment ago, that the viscosity controls the sound attenuation, or it controls how sound dampens and diffuses through the system. And if you have a metallic liquid that lives on a very weak atomic lattice, it is precisely the fact that a small charge perturbation, right, will actually set off a small pressure perturbation and therefore is coupled to the sound response, right? That shows you that the resistivity is controlled by the viscosity, or the sound is controlled by the same damping rate as that sound is dampened by. And then it's a small step by assuming that that you have Planckian dissipation and you have a linear in T entropy density, then you get a linear resistivity based on extremely simple assumptions. And moreover, extremely universal assumptions. You only need a linear NT entropy density, which we know from experiment. And you need the fact that you nearly saturate this bound, which is a universal bound, right? If Koftun, Son, and Starnets are to be. And then you get immediately a linear resistivity out.
You said it's a very weak lattice. Do you need to assume anything about the conductivity being very high or something like that, or very low resistance?
You don't need to assume anything. You just need to assume that you have a very weak, a weak lattice, which essentially you have there, but the appropriate then definition of what weak is and whether that's true in the system is a bit harder to specify.
Is it possible to determine or to get an idea of what you would measure in one of these metals? I mean, one of these strange metals, whether it is in fact a weak lattice or what is the
well? I mean, we don't know. Actually, literally, the two articles that I'm writing right now is using ADS-CFT to see what happens in a strong lattice, where we try to make the lattice as small as possible, and we try to see how this prediction changes.
Yeah, it's very, very interesting. Anything else you say about these topics today or tomorrow, we appreciate it. Thank you.
Okay, you're welcome. Any further questions?
Okay. I think it may be good time to close this.
Yes.
There are no more questions. Yeah. Let's thank Koenraad again for the nice lecture.
Yeah. You're more than welcome. It's a pleasure. Don't hesitate to also write me if you have a question. Like I said, yesterday there was a good question that required some work, and I'm happy to then answer it tomorrow. And I look forward to talking to you tomorrow.